The Elegant Universe, A Journey to the Edge of Our Understanding. Brian Greene's The Elegant Universe is a groundbreaking work that delves into the fascinating world of string theory, a revolutionary theory in physics aiming to unify all forces of nature. Greene, a renowned physicist, presents complex concepts in a clear and engaging manner, making the book accessible to a broad audience. The problem of unification. The book begins by outlining the problem of unification in physics. While we have separate theories for gravity, Einstein's general relativity, and the other fundamental forces, electromagnetism, weak and strong nuclear forces, we lack a single, unified theory that can explain everything. This lack of unification is a major challenge in modern physics. Enter string theory. Greene introduces string theory as a potential solution to this problem. Instead of point-like particles, string theory proposes that the fundamental building blocks of the universe are tiny, vibrating strings. These strings, smaller than atoms by a factor of a billion, vibrate at different frequencies, giving rise to the various particles and forces we observe. Extra dimensions. A key aspect of string theory is the existence of extra dimensions beyond the three spatial dimensions, length, width, and height, and one time dimension we experience. These extra dimensions are curled up and invisible to us, but they are crucial for the theory to work. The Elegant Universe. Greene argues that string theory offers a remarkably elegant and unified explanation for the fundamental forces of nature. It has the potential to explain phenomena like gravity, the origin of the universe, and the existence of dark matter and dark energy. Challenges and controversies. Despite its elegance, string theory faces significant challenges. It requires the existence of extra dimensions, which have not been observed experimentally. Additionally, the theory has multiple versions, and physicists are still working to determine which one, if any, is correct. The future of string theory. Greene concludes the book by discussing the future of string theory. He emphasizes the need for experimental verification to confirm or refute the theory. He also highlights the potential of string theory to revolutionize our understanding of the universe and the fundamental nature of reality. Key takeaways. String theory offers a potential solution to the problem of unification in physics. It proposes that the fundamental building blocks of the universe are tiny, vibrating strings. String theory requires the existence of extra dimensions beyond our familiar three spatial dimensions. The theory faces significant challenges but has the potential to revolutionize our understanding of the universe. Overall, The Elegant Universe is a captivating exploration of string theory, its implications, and its potential to unlock the secrets of the universe. Greene's clear and engaging writing style makes complex concepts accessible to a broad audience, making it an essential read for anyone interested in the frontiers of physics. String theory proposes the existence of extra dimensions beyond the three spatial dimensions, length, width, and height, and one time dimension we experience in our daily lives. These extra dimensions are fundamentally different from the ones we are familiar with. 1. Curled up and invisible. The extra dimensions in string theory are thought to be curled up on a very small scale, much smaller than the size of an atom. This is why we don't perceive them directly. Imagine a garden hose. From far away, it looks like a one-dimensional line, but up close, you see its circular cross-section, revealing a second dimension. Similarly, the extra dimensions are curled up and hidden from our macroscopic perspective. 2. Not directly experienceable. These extra dimensions are not accessible to our senses or to our current technology. We can only interact with the three spatial dimensions and one time dimension. Think of a flatland creature living on a 2D surface. It could move forward, backward, left, and right, but it would have no concept of up or down because it couldn't perceive the third dimension. 3. Mathematical constructs. The extra dimensions are primarily mathematical constructs within the framework of string theory. They are not directly observed, but their existence is required for the theory to work mathematically and to explain certain physical phenomena. 4. Potential for explaining phenomena. The extra dimensions are not just theoretical constructs, they have potential implications for explaining various physical phenomena. For example, they could explain the strength of gravity, the existence of dark matter and dark energy, and even the origin of the universe. In essence, the extra dimensions proposed by string theory are not like the dimensions we experience in our everyday lives. They are curled up, invisible, and mathematically defined. While their existence remains unproven, they hold the potential to unlock a deeper understanding of the universe and its fundamental workings. The relationship between extra dimensions in string theory and the concept of parallel universes is complex and multifaceted. While extra dimensions themselves don't directly imply parallel universes, they play a role in some theories of the multiverse, which is the hypothetical existence of multiple universes. Here's a breakdown. 1. Extra dimensions and brains. String theory suggests that our universe is not the only one. It proposes the existence of brains, which are higher dimensional membranes embedded in a higher dimensional space. Our universe, according to this idea, could be a three-dimensional brain within a higher dimensional space. Other universes could exist on different brains, potentially interacting with ours in subtle ways. 2. The brain world scenario. This scenario suggests that gravity can leak into extra dimensions, explaining why it is so weak compared to other forces. This leakage could also allow for interactions between different brain worlds, potentially leading to observable effects in our universe. 3. The cyclic universe theory. Some string theorists propose that our universe is part of a cyclic process, where brains collide and create new Big Bangs. This could lead to multiple universes, each with its own set of physical laws and properties. 4. The landscape of string theory. String theory allows for a vast landscape of possible universes, each with different configurations of extra dimensions and fundamental constants. This landscape could potentially explain the fine-tuning of our universe, where the values of physical constants are precisely balanced for life to exist. 5. Not a direct implication. It's important to note that extra dimensions in string theory don't necessarily imply the existence of parallel universes. They are a separate concept, although they can be incorporated into some theories of the multiverse. In summary, while extra dimensions in string theory don't directly prove the existence of parallel universes, they provide a framework for understanding how multiple universes could exist and interact. The brain world scenario, the cyclic universe theory, and the landscape of string theory all offer potential mechanisms for the existence of a multiverse, where extra dimensions play a crucial role. However, it's important to emphasize that the multiverse is still a highly speculative concept, and the existence of extra dimensions remains unproven. Further research and experimental evidence are needed to determine the validity of these theories. Testing the existence of parallel universes, especially those proposed by string theory, is incredibly challenging and currently beyond our technological capabilities. Here's why. 1. The scale of extra dimensions. String theory predicts that extra dimensions are curled up on a scale much smaller than the size of an atom. Our current particle accelerators, like the Large Hadron Collider, can only probe distances down to about 10 to the power of minus 19 meters. To detect these tiny curled-up dimensions, we would need instruments capable of probing distances on the order of 10 to the power of minus 35 meters, which is far beyond our current technological reach. 2. The nature of interactions. Even if we could probe these small scales, it's not clear how we would detect the effects of extra dimensions. The interactions between our universe and other potential universes, if they exist, might be extremely weak and difficult to observe. 3. The landscape problem. String theory allows for a vast landscape of possible universes, each with different configurations of extra dimensions and fundamental constants. This makes it difficult to pinpoint specific predictions that can be tested experimentally. 4. Indirect evidence. Scientists are looking for indirect evidence of extra dimensions by studying various phenomena like gravitational anomalies. Deviations from Einstein's theory of gravity could indicate the presence of extra dimensions. Cosmic microwave background radiation. Patterns in the cosmic microwave background radiation might reveal clues about the early universe and the existence of other universes. Particle collisions. High-energy particle collisions at accelerators like the LHC could produce particles that interact with extra dimensions, leaving unique signatures. 5. The search continues. Despite the challenges, scientists are actively exploring ways to test string theory and the existence of parallel universes. New theoretical frameworks and experimental techniques are being developed to address these challenges. In summary, testing the existence of parallel universes in string theory is a monumental task. Current technology is insufficient to directly probe the tiny scales involved, and the nature of interactions between universes might be too subtle to detect. However, scientists are actively searching for indirect evidence through various observations and experiments, hoping to shed light on this intriguing and elusive concept. String theory, despite its elegance and potential to unify physics, faces significant experimental challenges that hinder its wider acceptance. Here are some key challenges. The problem of extra dimensions. String theory requires the existence of extra dimensions beyond our familiar three spatial dimensions. These dimensions are theorized to be curled up and invisible to us at our current energy scales. Experimental verification. Detecting these extra dimensions would require extremely high-energy experiments, far beyond the capabilities of current particle accelerators like the Large Hadron Collider, LHC. Alternative explanations. The absence of experimental evidence for extra dimensions leaves room for alternative explanations for the observed phenomena that string theory aims to explain. Lack of testable predictions. String theory, in its current form, doesn't make many concrete, testable predictions that can be verified through experiments. Unification at high energies. Many of its predictions occur at energy scales far beyond the reach of current technology, making it difficult to test experimentally. Multiple versions. The existence of multiple versions of string theory, each with its own set of predictions, further complicates the process of experimental verification. The issue of falsifiability. Karl Popper's criterion. A key tenet of scientific methodology is falsifiability, meaning a theory should be capable of being proven wrong through experimentation. String theory's falsifiability. Some argue that string theory, in its current state, lacks sufficient falsifiability due to its lack of testable predictions and the difficulty of reaching the energy scales required for verification. The too many solutions problem. The existence of multiple versions of string theory raises concerns about its ability to be definitively proven or disproven. The need for new technology. High energy experiments. String theory requires new technologies capable of reaching much higher energy scales than current particle accelerators. Novel approaches. Exploring new experimental approaches, such as gravitational wave detection or precision measurements of fundamental constants, might provide indirect evidence for string theory. The role of mathematical consistency. Mathematical elegance. While string theory is mathematically elegant, its lack of experimental verification raises questions about its physical relevance. The beauty is truth argument. Some argue that the mathematical beauty and consistency of string theory suggest its validity, even in the absence of direct experimental evidence. The truth is beauty argument. Others contend that a theory's beauty and elegance should not be the sole criterion for its acceptance, and experimental verification remains crucial. In conclusion, the experimental challenges facing string theory are significant. While the theory offers a compelling and elegant framework for unifying physics, its lack of testable predictions and the difficulty of reaching the required energy scales for verification pose major hurdles. The development of new technologies and experimental approaches will be crucial for determining the validity of string theory and its place in our understanding of the universe.